Welcome. Let us continue from my earlier lecture straight away, and I was now talking about three phase induction motor. Okay. Suppose you have applied here line to line voltage root 3 V1 star connected machine. So, per phase voltage is V1, and what I am telling, this V1 will be approximately equal to the induced voltage, because stator impedance, leakage impedance is small, as I told you. So, it will be closely equal to this. Now, this phi then will be equal to V1 by root 2 pi f kW1 into L1. Okay. I will get this flux. Now, what I am telling, whether this secondary switch is closed or open, it does not matter. The flux per pole, this of course not phi max as in the case of a transformer, flux per pole has to remain constant. And what is this flux per pole? It is the corresponding to the net flux I told you last time, 4 by P B net L R. This is this flux per pole. Therefore, this flux per pole will remain same. In other words, the strength of B naught remains same practically, I mean from no load to full load operation. Of course, we have not explained what is full load operation here, but in other words what I am telling, no matter whether the switch is closed or you have connected some impedance on this side, this flux per pole has to remain same. Now, I am telling on one hand flux per pole has to remain same, and on the other I am telling I will close the switch, and therefore, there will be secondary current. Now, there is a second player coming into the picture apart from the stator to dictate terms, that is its MMF should also be taken into account, is not? Okay, flux per pole, how then it can remain constant? It can remain constant provided the moment you try to draw current, primary will draw enough current I 2 dash just like a transformer, such that the MMF or flux density created by this is handsomely balanced by the MMF which will be created by this additional current. That is the thing, that is how secondary current, any current is drawn on the secondary side of a transformer, primary current is automatically increased, because it has to satisfy the KVL equation here. Therefore, remember this B net value remains, magnitude of B net remains fixed, its position may change from one place to another, that is different issue, but flux per pole is remaining same. Now, why so much words I have spent? Simply coming back to this equation, we have seen that I 2 AC to actual rotor currents is like this, and this is the case when the machine is running. So, this is very quickly let me write, this is rotor, rotors are shorted, and suppose the rotating field is this direction, and rotor will also rotate in the same way. So, it is running with some slip S is equal to Ns minus Nr by Ns, that is fine, it is running, and this is the RMS value of the current. Okay. Now, listen to this point, this I 2 when it carries current, I told you it will create bear, and that too will be a rotating field. At what speed a stationary observer, stator coil will see this field to move at what speed? It is also ns with respect to a stationary observer in the same direction. Then only that torque angle delta can remain constant. Okay. It will move like that, and based on that it draws additional current to counterbalance that rotor rotating magnetic field. That is the whole idea. Therefore, rotor has to react on the rotating magnetic field created by the rotor and tries its best to nullify that effect. How it can do so? By drawing additional current from the supply, balanced 3 phase current I 2 dash drawn, and we will try to oppose that rotor rotating field flowing in this direction. That is the whole idea. If that be the case, let us consider, this is another step I am telling you, listen, this is the actual motor, this is the thing we are trying to analyze, draw the equivalent circuit. Then I saw that this can be written as E 2 by root over R 2 by S whole square plus x 2 square. This I wrote. Achha, now imagine an induction motor which is stationary, same stator winding, it is an imagined motor. Okay? This is very interesting point, imagined motor. You imagine a motor exists whose stator is same like this and whose rotor is also same like this, except that is number of turns this that are same, except that imagined motor its rotor resistance is equal to R 2 by S, where S was the slip of this motor. Please listen to me carefully what I am telling. This is the actual motor whose equivalent circuit I was trying to derive. Then I got stuck up at this stage. I find okay, secondary, there is induced voltage, fine, but there is a very unusual term, slip is coming. Therefore, it is difficult to I cannot join these 2 points here simply by multiplying this by S square, out of question, because I will always question this frequency is F, this frequency is S F. The ratio of the voltages is not also a constant number A, but it will involve S. So, there we got stuck up, and then we know the flux per pole in the machine has to remain practically same from no load to full load, whether you have connected something here or not. Then we understood okay, primary should draw additional current to counter the rotor rotating field produced by I 2, things like that. Now, what I am telling, this is the actual motor, stator field ns, rotor is moving nr and it is moving with a finite slip. RPM is present here, rotating machine. Now, what I am telling, imagine another motor, okay, whose terminals are shorted and rotor is locked, I will not allow the rotor to move, that is at standstill condition. Its per phase resistance, only thing I am telling, this is imagine that such a machine, okay, if it is there, whose rotor resistance per phase is R 2 by S, and what is this S? S is the slip of the actual motor we are discussing about. So, this is R 2 by S and its standstill leakage reactance leakage reactance is same as this one. It has got per phase resistance R 2 and standstill leakage reactance X 2 per phase. Now, for this fellow I am telling that I have another machine, suppose, whose rotor resistance per phase is R 2 by S, leakage reactance is X 2 at standstill condition, and this motor is stationary. Therefore, what will be its equivalent circuit? Here also I have applied V 1, here I get E 1, which is V 1 by sorry, this is V 1 applied voltage, which is approximately V 1. So, this circuit will be V 1 and this that, and the rotor circuit will be, what will be the voltage induced for this circuit? You have applied E 1 here, this machine is at standstill condition, this is important. Therefore, it will have an induced voltage E 2. This rotor is at standstill, let us imagine, and then it is closed, and what is the resistance per phase of the winding? Oh, I have told it is R 2 by S, fixed number for this machine, and there is a reactance here, leakage reactance. What is the value of this leakage reactance? I should write X 2. For this imagined motor, this machine is at standstill condition, its rotor resistance per phase I have imagined it to be R 2 by S, suppose, number of turns etcetera are same, flux in the machine per pole is decided solely by the primary winding, rotor has no say on that, supply voltage, supply frequency, what will be the flux per pole. Therefore, same number of turns k W 2 N 2, this I will maintain, this is k W 1 N 1, and this will be the situation. What will be the frequency of this voltage? F, because this machine is at standstill condition. What will be this reactance, standstill reactance, and this is R 2 by S. What will be the current? I 2, because you see I 2 is E 2 under root this impedance, same current will flow, but it will flow at 50 hertz. So, this 50 hertz current will flow. Now, the most important point, somebody sitting on the stator of this machine and this machine at standstill condition will not be able to distinguish whether it is a standstill machine with this parameter or it is a rotating machine with R 2 X 2. It will never be able to distinguish. Why? Because same current is flowing. So, rotor field produced by this machine and this machine will be of equal strength, and with respect to stator, this field is moving with synchronous speed and this field is also moving with synchronous speed. Therefore, stator should react in the same way, that is how much additional current it will draw from the supply to balance the rotor MMF in both the cases. There is no way rotor will ever know, I mean stator will ever know that it was a rotor was rotating at some slip s or some speed n r, and I have to draw an additional current. between these two machines, of which one is the actual machine with which we started and got disturbed, what to do, secondary and primary can be connected or not. Then I asked you, and then of course, I did some manipulation here, that is the RMS value of the current will remain same if you have an impedance of this kind. Then I am telling, okay, then let us have another induction motor whose stator is identical with that of this machine, but the rotor is at standstill condition and its resistance per phase is not R2 by S. The S with which the actual motor was running, and its leakage reactance at standstill is x 2, same as that of this machine x 2, and this machine is stationary. You apply a voltage V 1 E 1, then there will be induced voltage, because this is an induction motor, kW 1 N 1 by kW 2 N 2 will be E 1 by E 2, and it is at standstill condition. So, frequency of this rotor will have F frequency, that of the supply here, and its impedance is R2 by S x 2. The power factor of this circuit and actual rotor circuit of this machine E 2, which I drew earlier, R2 x 2 and R2. R2 by S x 2, actual machine. This is the current how we got. Now, in this machine, the power factor angle with which this rotor current will lag this voltage E 2 is tan inverse S x 2 by R 2. In this case, not only the magnitude of I 2 will remain same, but the power factor of this circuit is tan inverse once again S x 2 by R 2. Therefore, rotor in this imagined motor will have some RMS value of the current at some power factor angle with respect to E 2 will be same as this current of this actual induction motor, which is running at a slip pace and it is delivering a current I 2. This current I 2 with respect to this voltage will be also having same power factor angle. That is why I am telling stator will fail to recognize whether you have a rotor R 2 x 2 rotating with a speed nr, or this rotor is stationary now with changed parameter value, winding resistance is changed R 2 by S and it is stationary. The reflected current it will try to draw, because it has to react based on the rotor current, how much current it has to draw from the supply. With respect to stator, how rotor is recognized, and a rotating field has been created by rotor, it is moving with some speed, that is all at some power factor angle. And power factor angle is important, last time we also discussed. Therefore, it will be reacting in the same way in both these two cases. It cannot but do anything else. Therefore, what people do is this, that I will once again draw this. We had this one R 1 x 1. Okay, this is how I try to understand. There are maybe other ways. This is your x m and here is your E 1. On the rotor, actual rotor, it was AC 2, it was SX2 and it was R2, actual machine, and its frequency was SF. Now, I am telling, oh, this machine, this circuit is E2 divide by S X2, and this resistance is R2 by S, and pretend it is a stationary motor, pretend that it is a stationary motor at standstill. Then this frequency has to be F, it has to be F, a standstill motor. So, this two is simply not you divide by S, and because if you divide by S, what you do with the frequency SF. So, to translate this to this, then I am telling this motor with this secondary running with a slip S is same as the same stator, and the rotor is replaced by another induction motor whose rotor resistance per phase is R2 by S and X2, and stator will fail to distinguish between these two cases. Okay. This is I2 RMS value, this is I2 RMS value means its maximum value is also fixed, and maximum value of the current has to decide what will be the strength of the corresponding rotating field. 3 by 2 BR is not 3 by 2 B max something. So, it is RMS current, if you keep constant, it is same. Now, the question is, okay, somehow let us accept that, but there is another problem, means is these two circuits are equivalent in every respect. So far as current is concerned, it is equivalent. So far as the power factor angle of I2 in relation with AC2 is concerned and E2 is concerned, they are same, that is fine. But there is a massive important difference between these two. What is that? The thing is, in this circuit, what is the real power? In this circuit, somebody is sitting on the rotor, he will say power consumed in the circuit is I2 square R2. And in this circuit, the power consumed here will be I2 square R2 by S, which is not equal to that, real power is not same. In fact, it is larger, because slip is a number which is less than 1. So, this I2 square R2 by S is definitely larger than I2 square R2. Then how to explain that thing? I mean, what to do with that? Okay, now it is not at all surprising, because in this case the motor is running, and motor will be running with some slip which is not equal to 0 when there is an opposing torque. Mind you, this we explained last time. Had there been no opposing torque, absolutely slip would have been equal to 0, is not? Then this induced voltage is 0, current, no question of current, nothing. But when the motor has some opposing torque present, either in terms of frictional torque or opposing load torque, which acts in the opposite direction of T, then only there will be some finite slip with which motor will be running. It will, its speed will be less than synchronous speed. When it runs, then forget about this circuit. Here, if you are sitting, okay, here locally you will only say I2 square R2, but on this shaft the motor is running against a opposing torque. Some power is also dissipated there, that is the mechanical power, dissipated or utilized, whatever it is. So, I 2 square R 2 will be the copper loss in the rotor resistance, no doubt. But in this case, when it is running, I know I am running with a slippage, that means there is an opposing torque also. It is not only this electrical power, but also plus the mechanical power, which will be T opposing into 2 pi n r, that power. These two together are supplied. Therefore, the primary will draw sum of those two powers, and it does so because there is mechanical torque present. But in this case, what I am telling, I asked you to consider an imaginary motor whose rotor resistance is R 2 by S, x 2, and it is not moving. Therefore, no question of any mechanical power comes in, because mechanical power is torque into 2 pi n r. Motor must run to deliver the mechanical power, but in this particular imagined case, motor is not running. But as I told you, stator will not distinguish between this and this. This is also now corroborated by the fact that so far as total real power to be drawn from the supply in this case and in this case has to be same. That is why this R 2 by S will take into account both the actual rotor copper loss of the machine. In this case, suppose somebody says R 2 by S is the resistance and there is no mechanical power, story is over here. But coming here, I will tell, because I do this, it draws enough power. What will be the real power drawn? It will be I 2 square R 2 by S, corresponding to this real power will be drawn. Now, when I come back to this actual machine, I will tell, oh, this is the total real power drawn, which is greater than I 2 square R 2, it has to be, because it also supplies mechanical power. Therefore, it is not surprising that this power is not balanced in this circuit and in this circuit. But I will not be get disturbed by that, because I now know that in this machine, which I am telling standstill condition of that fictitious motor, its power loss is I 2 square R 2 by S. And since in the actual machine I 2 is flowing, so I 2 square R 2 is the copper loss, I know. Then I will say, oh, mechanical power per phase is I 2 square R 2. These are all the nicety about this way of thinking. So, this must be the mechanical power, and if it is 3 phase, multiply with 3 phase, that is all. And not only that, then these two can be combined. We will continue this in the next lecture. Thank you.